What up, nerds? I'm Bryson. You can call me Bammed, and this is CTF and Cigars, where I light up a cigar, I talk about CTFs, hacking, and just other security stuff. So I'm starting a new series. I used to be a trainer back in the day, not that long ago, but I spent about 7 years training security analysts, and so I've had a lot of experience like teaching and training people stuff. So I thought I'd actually do a training series, and part of what I'm going to do today is kind of based on something that I used to teach security analysts, but we're going to be more focused on reverse engineering. Before I get into that, I'm going to go ahead and light up a cigar. So today I've got this is the Flor de las Antillas. It's a Toro, which is 6 inches, 52 gauge, and this is by My Father's Cigars. So it's got a Nicaraguan filler binder and wrapper. I think I smoked one of these on here before, but the last time I had the Maduro, and this is the natural. This was Cigar Aficionado's Cigar of the Year in 2012. It's a pretty mild to sort of medium smoke. A lot of the flavors are pretty subtle. It's not bad. It's not super complex. You get a lot of the same flavors throughout. I know there's some cigars as you go, they kind of you get more complexity, and this flavor profile changes as you go. This is pretty solid all the way through. And my allergies are killing me, so I can't smell much. But I get a little bit of hay and cedar, sort of a little bit of mustiness, sort of earthiness on the pre-draw, the pre-light draw. A little bit of sort of a little leathery, a little bit of cedar again. And as we go through this, I think some of the main flavors that I usually get out of it are sort of a little bit of citrusy, let's hold on. I'm gonna check my notes again. Sorry, didn't get enough sleep. So a little nutty, a little citrusy. It's not too sweet. There's a little bit of maybe a nutmeg in there. But like I said, it tends to really sort of stay the same all the way throughout. It doesn't really get all that complex. Yeah, there's just a little bit of spice, a little bit of like pepper, but more like white pepper. Um, Slightly nutty, bit of cedar. It's pretty good. And if it's anything like the other ones I've had, it should pretty much stay the same the whole way through. Um, all right, now I've got that lit. Let's talk about what we're going to talk about today. So I decided to do a series on reverse engineering. So I'm going to go through and sort of do a training series on reverse engineering. But I wanted to start at like the real basics. So back when I used to train security analysts, one of the things that one of my that we had noticed. So I was working with another guy, and the both of us kind of working with these new analysts and talking through things was that while people do know about binary and they know about hexadecimal and they kind of understand what they are, they don't really have a good grasp of it. And no, that may not be you. You may have a great grasp. If so, this may not be the video for you. You may want to come back in a month or so when I've got more content around this whole reverse engineering topic. But I thought I'd just kind of go through some binary and hexadecimal basics today. So just kind of how those numbering systems work, so a bit of number theory, why they're called like base 2 or base 16, how you can easily convert those numbers, how you group them, and then also a bit about logic gates. And I kind of want to also show how different logic gates work together and how you can kind of build those on top of each other to define how a computer works. So that's the plan for today. I've also got a little bit of a game at the end of the show that we'll go through that kind of help you with the logic gate aspect of things. Then next time, I want to go more over CPU architecture. So talk about how modern CPUs work. And it's really where we're going to start looking into things like CPU registers, what those are, what they mean, and how you interact with them. And that's going to lead into a discussion on assembly language. So we'll look at x80 or x86 64-bit assembly language and kind of discuss how that works. We're not going to do a huge long primer on that. I'm not really looking into doing like binary exploitation. I may come back and do that later if there's some interest, which there probably will be if I do a good job at this anyway. But yeah, looking at the assembly, and then from there, I figured we could once we kind of understand assembly, look at the actual that are defined in the like the Intel manual on their processors and how those correspond to assembly. And I figured once we have that, maybe we can write a decompiler. So nothing super complex. I don't think we need to. I'm not really looking to build a useful tool out of that decompiler, but more a just kind of demonstrating how a decompiler works. We'll just put something in Python together, and really just enough in order to be able to decompile a simple hello world assembly program. So that's the next couple of months. So I've kind of got all that lined out. I still got to work the details out. But yeah, we're starting the series. But today's just going to be simple binary hexadecimal stuff. Maybe you already know it all. Maybe you don't. Maybe you learn something new. Hopefully, at least there's something new. But we'll see. So let's go ahead and get started. So I'm putting on my my trainer hat today. Put together a PowerPoint. So we can kind of go into this. So yeah, this is the beginning of my intro to reverse engineering, and today is BAM's binary basics. So we're going to talk about binary, we're going to talk about hexadecimal, and what those mean. So first off, we're just going to do some counting. So we've got binary. What is binary? Well, binary is a number system that only uses 2 digits, a 0 or 1. And you can represent all possible numbers. Well, sorry, all real positive numbers. With zeros and ones. Well, okay, you can represent other numbers, but it gets beyond just binary. We don't need to go into that right now. Let's just talk about binary. So we'll count. So you want to start counting with 0, and then after 0 comes 1, And this is where, if you're not familiar with binary, it's different than decimal because there's no 2. So what you have to do is move over to the next space. So it's like when you're counting 1 through 9, you've run out of digits, so you've got to have 10, which is 1, and then 0, so you're moving into a new space. So we follow that pattern. So then 3 is represented by 1, 1. And again, we're out of digits, we're out of spaces, so we've got to keep moving. So we've got 1, 0, 0. And 1, 0, 1, 1, 1, 0, 1, 1, 1. When I used to teach analyst and we did a class similar to this, my co-trainer, I won't mention his name because I didn't get his permission. He would recommend that you count in the shower just to kind of get familiar with how binary works. That was always what he said: count in the shower. So if you want to get more familiar with binary, yeah, I recommend counting in the shower. But yeah, just keeping through that pattern. So now that we were at the 4 spaces, we've got 1, 0, 0, 1, and then of course we go 1, 0, 1, 0, and then 1, 0, 1, 1, and then these, there's no more spaces here, so we've got to move to the next digit, 1, 1, 0, 0. Anyway, hopefully you kind of see the pattern there and see how that's working. If not, take a screenshot and just kind of go over it again and again, because this pattern continues. It's not that difficult, and I'll show you a little bit more about this in a minute. But that's just counting in binary. All right, now hexadecimal. See, I told you it's going to be very basic introductory stuff here. So hopefully it'll be useful for at least a few people. All right, hexadecimal is a numbering system that has 16 digits. So it's 0 through 9, but then we've got A, B, C, D, E, F. So those letters represent digits. So A would be 10, B 11, and so on. So again, we count like we would normally in decimal, 0 through 9. And then instead of going to 10 as in 1, 0, it's A. And then B, C, D, E, F. So F would represent the decimal 15. And then we've done the same thing that we did over here. We've run out of digits, so we've got to move to the next space. And so then what looks like 10 in decimal is actually the hexadecimal for 16. And then we continue following the same pattern of how you would normally count, 10, 11, 12, 13, 14. I hate to say those because they're not technically representing 10, 11, 12, 13, 14. They're actually representing 16, 17, 18, 19. But anyway, you see how the numbers are. And then we get to this 1, 9. Again, this is hexadecimal 1, 9. While in decimal, we'd go to 20. We still have more digits to put in this place. So we go to 1A, then 1B, 1C, and so on until we get to 1F. So 1F would be the F would be the highest number digit that we have in this place. So we then go over to the next place to the left and increase it by 1 to get 20. Now, we could keep doing this for a while, but let's go ahead and skip ahead. So let's say we follow that pattern until we get to 9F. So what do we do there? Do we go to 100? No. We've still got more digits in this place, so it becomes A0. And then the pattern continues. Skip a bunch more until we get to FF. So now we've got the highest possible digit in both places. So in decimal, it would be the same as if we're at 99. Once we have FF, then we actually go to 100. So I just wanted to kind of show that, just in case you're not super familiar with how the numbers work in binary or hexadecimal. You can kind of, hopefully you'll see the pattern. If you don't, go back, watch it again. It's not that difficult, but if it's not something you've worked with before, it might take a little bit to kind of grasp the idea, because we're so used to just dealing with decimal system. It might take a little more work. All right, now I want to break this out a little bit more and talk about bases. So decimal is base 10. That means the numbering system has 10 digits in it, 0 through 9. So let's take this number, 4,096, And let's kind of break it out. Now, you may have done something like this in grade school. I know I did. Hopefully you did too, just talking about number theory. But if we look at the first, the farthest right, the lowest number, lowest value digit in this number, one way we can represent this, so this would be like the ones place or the tens place. That's how we talked about it in grade school. But if we want to kind of break it out further, if our base is 10, then what this is saying is that the digit in this place is represented of or the value of it can be represented by this number. So 6 times 10 to, and then we start counting with 0. This would be the 0th place. So 10 to the 0th power. If you remember, again, basic math, 10 to the 0th power is 1. So we can, the value of the 6 in this place, 6 times 10 to the 0th, or 6 times 1, so it's 6. All right. So now we move to the next place, and so this is what we're talking about the base. Again, it's how many digits are in the numbering system, and then you can go through each place in a number and kind of break it out this way. So start with 0. Now we've got 1, and then you go to 2 and 3. So this digit 9 in this place can be represented as 9 times 10 to the first power, which is 9 times 10 or 90. This 0 here, it's 0, so it's going to end up being 0. But 0 times 10 to the second power. So if there was a 4 there, then the 4 in that place would represent 400. And then in this case, this 4 can be demonstrated as 4 times 10 to the third place, or 4 times 1,000, or 4,000. Add those together and you get the number 4,096. Again, this is probably like basic elementary school math stuff here. But just kind of wanted to show that in decimals so you get the idea, because now when we move to binary, it follows the same pattern and we can use the same rules. We just have a different base. So I'm going to just show you real quick how you can convert binary numbers to decimal. So we've got this number 1011, and I just put a B at the end of it to represent that this is a binary number. So we start here with this digit, that's that 1. And just like we did with the decimal, that first digit. So it's going to be 1 times 2 to the 0th power. 2 to the 0th power is 1. So 1 times 1 is 1. This 1 here can be represented as 1 times 2 to the first power. So again, we're doing the same thing. We've got 0, 1, 2, 3, and so on. So a 1 in this place represents this, is the same value, or the value of that is the same as a decimal number 2. Then we've got 0 times 2 to the second, which is 0, and then 1 times 2 to the third, which is 8. So if we have this 1011 in binary and we want to represent that in decimal, we just break it apart, add the numbers together, and you get 11. Hopefully that makes sense. Again, I expect if you've had any experience with binary, you're probably already familiar with this stuff, but just in case you haven't, again, just because I've encountered some people in my training days of security analysts who weren't familiar with some of these concepts. That's kind of why I wanted to go over them before we get into reverse engineering, where there's a lot of binary and hexadecimal stuff. I want to make sure everybody's got a good, solid foundation there. So we're doing the same thing with base 16. So this first digit is F times 16 to the 0th. I did go ahead and convert the F. F is equal to 15. So that's 15 times 1. So an F in the first digit of a hexadecimal number is equal to the decimal value 15. Then we've got 8. All right, my mouse is doing some weird things here. Hold on. Let me make sure you can see what I'm seeing. Okay. So we've got 8, an 8 here. So this is 16 times to the first power. Again, just like we did here in binary and here in decimal. That's how we're representing these digits. So 8 times 16 to the first is 128. A, since we're in this this place here, the third place, again, since we started counting from 0, that would be 16 to the second. So A is 10. So an A in this third digit is equal to 10 times 16 to the second, or 16 times 10 times 256. So it's 2,560. And then we've got this 2 times 16 to the third. Anyway, we do all that math, add all those numbers together, and we can figure out that the hexadecimal, and this 0x here at the beginning, that's just a way of notating it's a hexadecimal number as opposed to a decimal number. Sometimes it's obvious because there's, an A and an F in it, and we don't have those in decimal, but there doesn't have to be letters in it. It could be 2081 and still be a hexadecimal number, but if we don't notate that somehow, someone reading that value may not understand that it's hexadecimal, so we've got to notate it. The same thing with this 1011. So we're adding the B to show it's binary, 0x to show it's hexadecimal. But yeah, doing the math, 2A8F is equal to 10,895 in decimal. And this is how you figure that out. Or you can use a calculator. But definitely when you get more experience, you'll probably be using calculators. But I think it's good to understand how this works. Okay, now so a couple other principles here. How do you group data together in binary and hexadecimal? So you've probably heard some of these terms before, like bits and bytes. So we've got 16 binary digits here. A single digit represents a bit. So any single 1 or 0 in binary can be referred to as a bit. 8 bits together equal a byte. I think this is also pretty fairly common knowledge. A couple other groupings we can do. 4 bits are known as a nibble. So occasionally you'll hear that term. So that's a nibble. And then when we have more than one byte together, we can call that a word. And this is a 16-bit word. The size of a word kind of depends on the architecture you're looking at or the particular circumstances. There are different size words. This would be a 16-bit word or a 2-byte word. All right, then we've got hexadecimal. And this is where things get kind of interesting here. When we see the reason why we use hexadecimal frequently in computer science is because there's a very definite correlation between binary and hexadecimal. So binary, 1s and 0s, those are easy things to create in an electrical circuit. 1 is on, 0 is off. Now, it gets much more complicated with modern computing technology, but that's essentially what it all kind of boils down to. You're looking at a circuit, you input some values, you output something. If the output is 1, it's on. If it's 0, it's off. But as we group these together, with hexadecimal, it all kind of lines up really well. Plus, we can get much larger values with much fewer characters. So like if I tried to write out A2, B4, 0D, 78, dead beef. In binary, it would be, a much longer number than what we can see here, and it'd be kind of hard to read. So this just makes things easier to read. But yeah, so how do we break out these? Well, there's a reason why I spaced it the way that I did. Any 2 hexadecimal characters are equal to 1 byte. So there's a direct correlation. If you have 8 bits, 8 bits can represent any number, any value in decimal from 0 to 255. But which is 1 byte. So there's a byte can represent any value to 0 through 255. In hexadecimal, 2 digits also, 0 through FF. 0 is, of course, 0, and FF is 255. Once you get to 256, you've got to move over to another digit. So it's really easy to break apart 8 bits into just 2 hexadecimal digits. And a nibble is just half of that, so it's just 1 single character or digit. So any single digit in hexadecimal is a nibble. And then, again, we have words. And like I said, there are different size words. So in this case, we've got an 8-byte word or a 64-bit word, which if we're looking at 64-bit architecture, you're going to see data kind of represented in that format. All right. So why should I care about all this? Well, there are going to be times when dealing with computer science where the data is going to be represented in, maybe a 64-byte word, but it's fitting a specific data structure where you actually need to know what individual bits inside of it are. And if we go back here, one thing you can't do in hexadecimal is actually show the value of a specific bit by the hexadecimal. You can figure it out, but you're going to have to convert it from hex to binary. So that sounds really hard. When you get to really big numbers like this, if this is the whole number and you want to convert that to binary, there's, if you're doing it the long way, converting it to decimal, then converting that to binary, that's a lot of math. So there's an easier way to do that. So if we take this hexadecimal value, dead beef, all we have to do, since a single character represents a nibble in hex, and a nibble is 4 bits, then we only need to convert each character by itself. So we don't have to figure out the entire value of this 4-byte word. We just need to know that D is 13, or in binary is 1101. E is 14, or 1110. And we can continue doing that all the way through for each character. Now, once we got to the end, we have the full binary of dead beef, and we didn't have to do any complicated math. All you have to know is 0 through 15, in binary and in hexadecimal, and you can convert any size hexadecimal value to binary. It's that easy. You only have to worry about a single nibble at a time. And the same thing with binary. You can convert it back. So if we have this binary value, we start with 1110. Well, that's 14 in decimal, or E in hexadecimal. 0110 is 6, which in 6 in decimal and hexadecimal are represented by the same digit. And we can go through and just do each nibble at a time and convert this, let's see, what is this? 32 bits into hexadecimal very simply. So if you weren't familiar with the way binary and hexadecimal kind of correlate this way, I think this is probably the most important thing to kind of get out of this, is that there's a very simple way to convert directly from hex to binary and binary to hex. And this is why we tend to represent data in computer science in hexadecimal, because it's just you can display more data in a smaller space, and it's very easy to go back and forth with binary. So another topic, just to kind of point out, there's something in computer science known as Indianness, and that's a discussion on the order that you represent bytes in memory or in a file structure or whatever the case. So there's big Endian, which means the most significant byte is first, and then there's little Endian, which has the least significant byte first. Okay, well, what does that mean? So I've got this number, and I got the same number in big Endian or little Endian. Right now, I'm just showing you the decimal value, and I'm going to convert this to hexadecimal and display in big Endian and then little Endian. So in big Endian, it would be dead beef. And what we mean by most significant byte first. So if you start with the this DE, here we go. That's what I'm looking for. So DE in this location in big Endian is equal to this large number. Was this 372,454,000? Nope, I got 3,724,541,952. So this byte is the most significant because it has the largest value. And so in Big Indian, you display that first. And while the last byte, EF, is the least significant byte, because this EF in this place in Big Indian is equal to 239. Well, 3.7 billion is more significant than 239. So you display it first in Big Indian. But in Little Indian, you display the EF first. And again, it's not just reversing the value. It's reversing the byte order. So the question is, what's the purpose of Little Indian? So I would say it has to do with sort of optimizing how data is read, and it's yeah, I don't have a great example. It's kind of arbitrary. I would say in the early days of computing, the order data was read in probably had a fairly significant impact on the performance of the computers. Nowadays, not so much. And it is sort of arbitrary. However, once you've chosen your Indianness, you've got to stick to it. So in TCP/IP, if you're looking at like raw packet data, it's going to be in Big Indian. But if you look at the x86 CPU architecture, it's actually reading data in Little Indian. And at some point, when we're actually doing some debugging and we're looking at the data structures in memory, we'll see that. We'll see how the least significant byte will be shown first. And I don't have a great example of how that's helpful. Again, it is fairly arbitrary. I'm not sure there's a great benefit of one over the other. Well, I would say for Big Indian, you're reading data over packets in TCP/IP, and so the way the packets are structured, as the data is read in, the kernel can start processing that data as it comes in, and you've got things like how is it supposed to be routed, so you can actually start making routing decisions before the entire packet is read in, things like that. Least significant bit, I don't know, it's a little bit harder to really think of where that's super useful, except maybe if you're doing some like math calculations, your least significant byte, so like the if we go back to like grade school math and you're adding 10,556 plus 794, you start with the farthest right digits and you add those, because 4 plus 6 is 10, and then you carry the 1. So it's basically, if you kind of think of it like that, when if you're adding in that manner, you start with the least significant digit and then you move over. And so if you've got a CPU and it's working with this data, it might be able to benefit, at least some performance wise, from reading in the least significant byte first, because that's where the first calculations are going to occur. So I'm sure that's a way oversimplified explanation, but hopefully that helps. All right, so now we're going to talk a little bit about logic tables, and then I've got a little game we'll kind of go through. So logic tables, these are ways of, all these logic tables are things that can be represented in circuits. And by combining them, you can actually build on them and basically define everything that happens inside of a computer. And I'll kind of touch on that here in a minute. But let's start with the basics. So we've got binary. So we've got a value A, 0, of course, is equal to 0, 1 is equal to 1. Now we look at AND. So AND is a binary logic function. And in electrical engineering, this would be sorry, I'm not great at electrical engineering, but like an inline circuit where, like, say you've got two switches, I mean, a very basic way of representing this is you've got a light, a power source, and you've got two switches, and one switch is connected to another. So both switches have to be on in order for the light to turn on. If either of the switches are off, then it breaks the connection. So this is what an AND logic table looks like, and it again be represented by an AND circuit. So 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. Again, thinking about this like an electrical circuit, you've got to have both switches on to actually have the final value of on, one being on in your circuit. So we've got not, which is just inverting a symbol or a value. So not 0 is 1, not 1 is 0. Or, which would be like a circuit that's in parallel. So you've got power source and you've got two switches, but the switches are independent of each other. So if either switch is on, the light is turned on. So this is 0 or 0, 0, 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1. Nor is just not or. And if you look at this table, what we're showing you, we've got A, we've got B, we've got A or B, and then we're doing the not of that. So just the inverse. XOR is a little bit more complicated, not terribly so. And XOR is really useful because if you can reverse it, and so it's a very basic encryption mechanism that you actually see a lot of malware, and actually there's a lot of encryption schemes that'll use XOR. So this is an exclusive OR. If we want to sort of like and or and not, those are things that we can just like say in English language and are like super obvious what they mean. An exclusive or, I think the best we could come up with is a phrase like it's A or B, but not both. So if we've got 0 XOR 0, the value is 0, but 0 XOR 1 is 1, 1 XOR 0 is 1, 1 XOR 1 is 0. So it can, if either one of them are 1, the value is 1, but we can't have both be the same value. And then we've got NAND, which is a not and. And NAND is super useful because you can actually start with NAND and you can build other logic gates on top of that. And basically you can actually then from there build an entire computer. And that's where we're going to kind of pick up here in a second. So this is just not and. So if we look at our and table, we just take that table and then we invert it. So not 0, not 0, not 0. And that's NAND. All right, so that's the end of the PowerPoint. Now, what I kind of wanted to go from there, there's this course that I took a long time ago. And by a long time ago, I think it's been over a decade since I took it. And it's called NAND to Tetris. Let's see, from NAND to Tetris, building a modern computing from first principles. Let me share this window here. So let's see. There's a book here. Let's go ahead and I think this should be their site. Yeah. So there's a professor put this together. And what this course does is you start with a NAND logic gate, and then you use something in the course. They use what HDL, which is hardware descriptive language. There's a program that you supply. It's all kind of stuff that these people, Noam Neeson and Shimon Shacham, have built. And they've essentially built a CPU architecture. But as you go through the course, you do as well. You start with NAND, then you combine multiple NAND gates together and use this hardware descriptive language to do this. So that would be like a sort of pseudo code that defines what hardware was doing. You combined NANDs and you can get a not or an and an or. You keep building on those Eventually, you build out an ALU, you build out a whole CPU. You define opcodes and a assembly language, and eventually you actually get to where you're building the game Tetris, just starting with NAND, and everything that you use beyond NAND is just you building on the previous task that you've done. So there's this game called Nand Game, and it's just nandgame.com, and it kind of walks you through that. So in the course they use HDL, but then more recently they've come out with this game online, so you can kind of visually see how this stuff works. So our first task is to actually build a NAND gate, and so we're going to start with just a couple of relays. So if you've done any electrical work, if you're familiar with anything related to sort of electrical engineering, you know what a relay is. Or if you don't know what a relay is just a switch. It's an electrical switch. So it's got two inputs and one output. In this case, the C here is the input that controls the switch. So we've got a default on and a default off, or a default open and default closed. Well, reverse those. Default off would be default open. Default close would be default on. So we'll drag this here. So we've got some power over here. We've got this this input here that represents the switch part of the relay, and then this is the this if you well, all right. If you look here, you can see this represents a open circuit, so it's not connected. So if we have a current coming through this input, it's just going to stop there. It's not going to go anywhere. However, if this switch is closed, then the current will go through to the output. So think of, again, 1 is yes, there's current. 0 is no, there's no current. So like if I connect this to power, you'll see the circuit now is closed. And right now we have no input, so it's 0. But if we link up the input to the current, we can now see that's 1. If I remove it from the current, the switch opens. The current stops here because the circuit's not closed, and so the value is 0. So the idea here is we're going to take these relays, and then this relay is the opposite, where it's default closed, and so when you apply current, it flips the switch, and now it's open, and so the value is not going through. We're going to take these, and we're going to demonstrate how you can use these two relays in order to build a NAND circuit. So we've got this open relay. Right now, there's no current that's going through this, so the output is 1. If I provide current to the input, the switch is open, but so there's no current actually getting to the output. So even though we have a 1 coming in, the output is 0. Now, if we close it, then you can see it flipped the switch when we applied current here. So I made a 1. Again, 1 means current, 0 means no current. And now the value is actually getting through. So that's a relay. Now, how are we going to make this to a NAND gate? Well, what we can do is we can take that output and make it the input of our, to get this to line up right. So this is actually going to control whether or not the relay actually switches. And I think if we connect that should work. There we go. So now we can kind of see how this works. In a NAND gate, 0 NAND 0 is 1. So since this is default closed or default on, we're just providing a constant source of current to the input, which means that the switch, the circuit's closed, and so that 1 gets fed all the way through. Now, if I add a 1 to either one of these inputs, we've got 2 inputs, A and B. So I can add a 1 here, and we can see, okay, now we have an input of 1. However, the output of this is still 0. And again, this output will determine whether or not this particular relay flips. So as long as the output of this is 0, then the output of this relay is going to continue to be 1. So we've got our 1 here, but the circuit's open, so it's not getting through. If we do the other way, we've got a 1 here, but this is a 0. All right, we've now closed the circuit, but there's no current coming through this input, and so the value remains 0. The switch remains closed, and it continues to be 1. So we've got 0 and 0 is 1. 0 NAND 0, 0 NAND 1 is 1, NAND 1 0, 1 NAND 0 is 1. But now if we flip both of them on, so we've flipped this switch, so we've now closed this circuit. This current is going to get all the way through. It's going to come here to this relay. It's now flipped this relay so that it's closed, and the value is 0. And that is a NAND circuit. So you can get just a default open and a default closed relay, solder them on a board, and you can literally make a NAND circuit on a circuit board. Hopefully that makes sense. All right, let's look at the next level. I should have cleared these up. So now we have a NAND gate. And again, this is kind of how the NAND to Tetris course goes. But we've built the NAND gate. Now we've got a NAND gate. We want to try to build something else. So they're calling this an inversion or an inverter. Basically, it's a NOT. So we can take the NAND, and we've got, in this case, we've only got a single input. So a NOT is just the invert of a value. So 0 becomes 1, 1 becomes 0. If we go back, let's go back, look at our NAND logic table here. So on a NAND circuit, since we've only got one input, what we can see is if both inputs are 0, the output is 1. If both inputs are 1, the output is 0. Well, that works really well for an invert, for our invert circuit, because we've only got one input. So all we got to do is drag both the inputs to our output here. So we've got 0 NAND 0. Well, that equals 1. So not 0 is equal to 1. Now we've got 1 NAND 1. Well, that's equal to 0. And so in not 0, or the invert of 0, the invert of 1 is 0. So now we've taken a NAND circuit, and by the way we've wired it up, we now also have a NOT circuit. All right, let's clear this one. So hopefully you can kind of see what we're doing here. I'm not going to go through the entire course. You might want to check out nandgame.com, start playing around with it. And then if you really kind of want to get into this, I'm just looking at basic logic gates here, but it really does start building on that, getting into how you can do math and other things. Let's just do an and real quick, and then maybe we'll jump ahead a little bit and look at how you can do some math. So if you remember, NAND is not AND. So really all you have to do is wire up the NAND circuit and invert the output. And that's all you're doing. So 0 NAND 0 is 1. Invert that, becomes 0. Well, 0 and 0 is 0. And as we continue going through that, 0 NAND 1 is 1. Again, inverts become 0. 0 and 1 is 0. So that's our output. And then when we have both 1 NAND 1 is 0, invert that, we get 1. And now 1 and 1 is 1. So we've made our AND circuit. All right. Well, we can keep doing this, and you might want to give that a try yourself. But let's look at how we can do some math once we've got these basic circuits. Okay. Cigars getting a little uneven here. So we're gonna do some math, just using logic circuits here. Get to the label and take that off. All right, so our little math table here, we've got two inputs, and the output is actually just going to be 2 bits. So it's not 2 outputs. What we're looking at here is going to be the actual 2 bits that represent our value. What we're going to do is we're going to add. And this in the course they just call this a half adder. We're just going to add 2 bits. So 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And then 1 plus 1 is 2, which in binary is represented by 1, 0. So we've got to think about how this works. And if we just look at, I would say the way to look at this is to look at the value that's returned for each bit in our output. So if we're adding 0 plus 0, the first bit is going to be 0. If we're adding 0 plus 1, our first bit's going to be 1. If we're adding 1 plus 0, the first bit is going to be 1. If we're adding 1 plus 1, the first bit is going to be 0, because the value 2, we've got 1, 0. Now, if you ignore this column and look at this as a logic table, what does this look like? Well, this looks like XOR. So 0 XOR 0 is 0. 0 XOR 1 is 1. 1 XOR 0 is 1. 1 XOR 1 is 0. So what we can do to calculate our first bit is just have an XOR circuit that outputs to the rightmost bit in our output. Now look at this leftmost bit, and again ignore the rightmost bit. We've got 0, 0 is equal to 0, 0, 1 is equal to 0, 1, 0 is equal to 0, 1, 1 is equal to 1. So what does that look like? Well, that looks like an AND table. So 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. A lot of numbers in this episode today. But anyway, so we can just figure out the second value or the leftmost bit in our little half adder by adding an AND gate. Put that in there, and that's it. That's how you do basic, simple 2-bit math, just using logic circuits. So if we have again, these are 2. This isn't a number, but these are 2 separate bits, and then this output represents a single number. So if we have 1, well, our value is 1. If we have a 1 here, again, we're adding 1 plus 0, the value is 1. If both of them are 1, 1 plus 1 is 1, 0, or 2. So there's some basic math. And it gets more complicated if you start adding more digits. This is a full adder. But I think that's good enough for now. That'll work. All right. So if you find this logic circuit stuff interesting, I definitely recommend you check out that Nand to Tetris. Well, there's the Nand game. That's nandgame.com. If you go to the About section, it'll take you to the Nand to Tetris course. There's some software you can download that lets you do the HDL, hardware descriptive language. Now, I've seen some people kind of naysay this course because it They say it oversimplifies how CPU architecture works, and this isn't exactly really how CPUs work nowadays, which is true and is valid. But I still think it does demonstrate a lot of important principles, a lot of basics in how computers think, and how they operate. And I found it worth the time. So, if you want to check that out, that's up to you. I'm not going to go through everything. There's already a course here. It's done really well. You can check it out, do your thing, figure that out. Or just, come here and play with the Nand game and see what you can figure out from that on your own, or by reading tutorials, or whatever you want to do. So that's enough of that. And I think that'll do it for this week. So I'm going to start putting together a presentation probably in a couple weeks. If I'm not doing anything that weekend, I'm going to come back and we're going to talk about modern CPU architecture. So the whole NAND game, NAND to Tetris stuff, it's again just kind of an oversimplified, but it gives you some good building blocks for understanding how CPUs work and how computers work as a whole. So feel free to check that out. That's somebody else did that. I have no relation to them whatsoever. It's something I got a lot of benefit out of. But yeah, in a couple weeks, we're going to start talking about the Intel CPU architecture, about CPU registers, those sorts of things, and give you the rest of the building blocks that you need so we can then start looking into assembly. So next time I come back, we'll talk about CPU architecture. Then after that, we'll start an assembly primer. I haven't worked out the details. I'm not sure how many episodes or how long we'll go through that, but all that eventually to build up into building a decompiler that we'll make ourselves in Python. And then from there, we'll actually get into some more modern reverse engineering tools. So the reason I wanted to do things this way, I have taken some, reverse engineering courses in the past couple of years, and well, been longer than that. But anyway, a lot of them seem to just kind of start in the tools. Like here's IDA, here's Ghidra. Actually, when I first did reverse engineering course I took, Ghidra didn't even exist yet. But here's OllyDB, or OllyDBG. And you just kind of start walking through those tools. But I think you've got to really understand a lot of this kind of low-level stuff to get the full use out of them. Yes, you can open a tool and you can start playing around with stuff and you can start picking up on patterns and recognizing things. But I've always been the kind of person who needs to understand not just what to do, but why you're doing it. What does it actually mean? And so that's what I'm trying to do here by kind of building up some of these basic building blocks. And it may be boring. It may seem to go on too long, but I'm hoping it might help somebody out there who wants to get into reverse engineering. So thanks for watching. Hopefully somebody learned something. And I will say next time that you're in a CTF, don't forget to try harder, don't panic, and always RTFM. Thanks. Bye.
Amendment to Mount Sight.